Hey there. So today I want to talk a little bit about notation because I really want to define the way that I write out math in like a very clear and succinct way with a set of rules that I really try to be very consistent with. Uh, because so far I don't think that I have been. Um, Hey there. So today I want to talk a little bit about notation because so far on this channel I've been pretty wishy-washy with my notation. I haven't really been holding myself to a high standard with my precision, and I really want to try and change that. I want to, be very standardized and clear whenever I write, a mathematical expression or a statement in physics or, whatever that I'm looking at. So I really want to make this video to kind of put some guidelines down before going forward. What this video is not going to do, it's not going to explain all of these ideas very clearly. Like if I say an integral, I'll write that out in English and say that when I write this symbol, I'm talking about an integral, but I'm not going to go into, what that means. This is purely just a set of symbols and rules for me to follow when I notate things, because at the end of the day, I need to be consistent with basically math as a language. So with that, let's go ahead and introduce. For this video, I'll use R. This is going to be my generic variable. Or my generic function. Okay? So let's first talk about how I will use scalars. So if I don't put anything over the R, this immediately tells you that this is a scalar value. R, of course, could be a function of a single variable like t, and we would say in English that this is R as a function of t. And when R is a function of a single variable, we can write its derivatives with a lowercase d. dr over dt, just like this. And this reads out to be the derivative of R with respect to t. If t happens to be time, which in a lot of situations in physics it is time, then dr over dt can be written as r dot. So this dot is a time derivative. Okay? R could be a function of multiple variables too. For this video, I'll always write 3 variables. Those will just be x, y, and z. But realize that I could keep writing more and more variables that R is based on. So this translates in English to R as a function of x, y, and z. And I could take the partial derivative with respect to any of those variables, right? So when we're multivariable, instead of using these lowercase d's, I use these kind of curly d's. Oh, whoops. Wrote that out all wrong. There we go. So these are all partial derivatives. So in English, this would read out as the partial derivative of r with respect to basically blank, where the blank could be x, y, or z. Okay? We've been talking a little bit about, this dr over dt, my rates of change. So let's just talk next about what a dr would mean. So when I use dr, this refers to an infinitely small change in r. When I use the symbol delta r, this could be written as the integral from r naught to r final of dr, which is the same thing as r final minus r naught. This refers to a finite change in r. Say that r is a function of one variable, which I said would be t. Then we can write out integrals of r with respect to t. This would translate to, in English, my integral of r with respect to t from t naught to t final. And really, if we wanted to be extra precise here, this is the definite integral because it's on a defined region. Okay, next, say that r is a multivariable function, like of x, y, and z. Then we could define a multi-integral, in this case a triple integral. This would be r as a function of x, y, and z. We would have dx, dy, dz, and we define our boundaries for all three. And this would translate in English to integral of r with respect to x, y, and z from x naught to x final, y naught to y final, z naught to z final. Okay? And then finally, if I ever use a D with a line through it like that, this refers to an infinitely small amount of r. That's different than just a regular dr, which is an infinitely small change in r. This is an infinitely small amount of r. Just to give a quick example of that, because that might be a little confusing, situations where we would use this would be in the definition of power as a small amount of work done over a change in time. The reason why we word it like this is because, like, when I'm pushing a block, I'm not changing work, I'm just doing an amount of work on that block. Okay? But anyways, this is a pretty special situation, so I would try to be very clear in whatever video I was talking about this guy in. Okay, so that covers pretty much every way that I would talk about r as purely a scalar value for right now. Okay. So the next thing before we go any further, let's go ahead and just do logic symbols. And I'm not going to spend a whole lot of time on this because most of the things I like to write out in English anyways because I think it's more clear. So the only ones that I'm really going to talk about are the equals, this little triple equals thing, and this guy. So the left, we already all know that this is just equals. The middle, whenever I use this, this is a definition. This translates to is defined as. Right? So for example, if I'm talking about velocity, velocity is defined as this guy, right? Which again, this is not a physics video, it's just a notation video. But that's how I would say something like that in English. As soon as you plug numbers into something, if I get an expression of, I don't know, let's just say there was a force, somehow I got something that looked like this, and then somebody said that x, you know, you happen to measure to be like 5.1, y you measured to be 3. As soon as you start plugging numbers into things, chances are you're going to approximate a numerical value to something. And that's what these squiggly lines means. This is approximately equal to. Alright, so with those out of the way, next let's talk a little bit about vectors, how I'll write vectors. So for r, if I put an arrow above it like this, this indicates that this r is a vector. And again, vectors can have any number of components, but I think it's easiest to just go with 3, an x, y, and z component. So I could write out r as a row vector. So rx, ry, and rz, like this. And I could also write it with unit vectors I, j, and k hat. These are all equally valid. I'll always try to write out my vectors in row form, not column form. You could write out your vectors like this, but I'll avoid that for the most part. My vector could be a function of another variable. So r could be a function of t still. And in this case, that would mean each of its components, Rx would be a function of time, Ry would be a function of time, and Rz would be a function of time. We could take the derivative of r with respect to time, and this would apply a derivative to each of the components of my vector. Which, from before, we said that this would be equal to just putting dots over them, where the dot indicates a time derivative. Right, so just to re-emphasize that point. Okay? R could also be a multivariable function. In which each of the components would now be, Each of the components would now also be multivariable functions. And usually in these situations, we'd be talking about vector fields. Because think about what this is saying. If I have some space in x, y, and z, that depending where I am in space, that's changing my vector r, right? That's what you're really saying. And so, going around in the x, y, and z directions is going to generate a bunch of different vectors, and that in effect creates a vector field. All right, awesome. Next key thing when we talk about vectors, let's say that I have two vectors. So for my next vector, I'll introduce s when I need a second symbol. So we could have r dot with the vector s, and this symbol is referred to as a dot product. Or this is just the dot, but this situation, we're taking the dot product of r and s. This, by definition, is r, like the matrix r, times the transpose of s. So what does that mean? So if we think of r and s like vectors, then rx, ry, and rz would have components like that, and s would have components sx, sy, sz. And so to multiply these two together with raw matrix multiplication rules, we would have to take rx, ry, and rz and multiply it by the transpose, which means to take our row vector and turn it into a column vector, sx, sy, sz. And then we simply use multiplication rules to work this out. And we would get rxsx plus rysy plus rzsz. And again, this is why I use my definition, or why I write my vectors in row form, so that this guy right here makes a lot more sense. As you can see, we put in some vectors, and this outputs a scalar value. We could also take what is called a cross product. So whenever I use this x, I'm referring to a cross product. And this is defined as a determinant where I put my I, j, and k unit vectors in the first row, my rx, ry, and rz components in the second row, and the sx, sy, and sz components in the third row. This also indicates that this symbol here is how I will represent determinants of matrices. Sorry. The only other things that I could really think of to talk about with this section would be line and surface integrals, but I think those are more complex to the point where I'd really discuss them in depth with whatever physics concept that I was thinking about. Okay, the next section I want to talk about is just the del operator. Because this could be used in situations where r is a scalar or a vector function. So let's start with if r is scalar. Actually, before we do that, let's just say kind of what a del operator contains. So let's say that my components of my function are still x, y, and z. Then this del operator would be defined like this. Partial derivative of something with respect to x, partial derivative of something with respect to y, partial derivative of something with respect to z. Those somethings depend on how this del operator is used. So now that we have that, let's go ahead and say if r is a scalar function, then del r, in English this would be the gradient of r, would be defined as dr over dx, dr over dy, dr over dz. Now let's just be super explicit in this first statement and clarify that r is specifically a function of x, y, and z here. There we go. Okay, next, if r is a vector function, then we have two separate definitions. The first is the divergence of r, which is defined as the gradient dotted with r, which let's imagine what that would equal. take this guy and we dot it with R, which is made up of Rx, Ry, and Rz components. Then this guy would equal drx with respect to x plus dry with respect to y plus drz with respect to z. That's what the divergence of a vector field R refers to. Right, so this vector function, we could also call this guy like a vector field. But again, context is really going to be important with situations like this. We could also define the curl of our vector field R. And this would be defined as the gradient cross R. And if we remember what our cross product looks like, then we know that it's a determinant. Put I, j, k unit vectors in. And we have d blank for dx, d blank over dy, d blank over dz. And we have rx, ry, and rz in here. And then we just apply these partial derivatives using determinant rules. Again, it's very frustrating for me with this video because I'm not explaining any of these mathematical ideas, I'm just writing them out for notation. But I do want to explain out all of them, but that would just take too much time. This is purely just how I'm going to write things out in the future. Okay. The final point that I want to talk about has to do with averages. So let's go ahead and say if dr over dt, let's say that we defined this as some variable s. If I have nothing over s, actually, in this case, I've been using, whenever I talk about r being a function of t, it's always been a single variable. So let's be like this. So this is defined as some other variable s. And a lot of physics comes down to just defining rates of change as another variable. Of course, here, this is referring to an instantaneous rate of change. So this would be an exact value for s. So if we set up a situation like this, then delta r over delta t, this is now an average change of r with respect to t. Well, actually an average rate of change of r with respect to t. This guy would be defined as s, and I'd put a bar over it. Just a straight bar. Not to be confused with a vector symbol. So whenever there's a bar, I'm talking about a calculus definition of an average. S bar could also be written out like this. The integral from S naught to S final of S as a function of t dt divided by t final minus t naught, or just delta t. The reason for this being is very simple. Say that we have, like before, s equals dr over dt. We can move the dt to the other side. Be left with dr. We could integrate both sides from t naught to t final and r naught to r final, and we would get r final minus r naught equals this integral. This, of course, is delta r, and so I would be able to just take this integral and plug it in to delta r. And that's all that I'm doing with this statement here, is I'm just taking this guy and plugging it in for delta r. So these are all equivalent statements. These two statements right here are equivalent. Okay? So if you ever see a bar, I'm referring to our calculus definition of an average. The next thing is if I use brackets. If I go like this and put brackets around R, here I'm referring to a statistical definition of average, or specifically the mean. Whenever I talk about this, I'm saying that this is defined as summing up all of my data points and then dividing by the number of data points. I know that stats can get more complicated than that, and you can have continuous distributions, but that's not I don't want to overcomplicate this. The point is that when I use brackets, I'm referring to the mean of something. This is going to make it very easy when I'm talking about the mean of like r cubed, or some more esoteric things. The things that are inside the brackets are the things that I'm taking the mean of. All right. So with that, I think we can see the differences between when I'm talking about my calculus definition of average and my statistical definition of average. I'm really going to try hard to adhere to this kind of strict way of writing things out. And again, I'm not expecting that like anybody matches my exact way of writing all this stuff out. I know that this video is very dense, very heavy. This is more for me actually than just for some random person watching. But I really want to try to adhere to this writing going forward. So with that, thank you so much if you actually put up with this and watched the whole thing. And yeah.